Hello, and welcome back to CS631 Advanced Programming in the Unix Environment. This is the final video segment for our Week 2 materials. After having discussed the 5 essential syscalls responsible for almost all file I/O in Unix in our previous segments, we'll now take a look at what it means when multiple processes access the same files and what the implications of that are on the syscalls we know. We also look at a few additional functions relating to file I/O and file descriptors. But after all this, you will be all set to go and work on your first homework assignment, putting to good use what we've learned so far. Let's get started. As we know, Unix has been a multi-user, multi-processing operating system from its inception. That of course implies that multiple processes may be accessing the same resources, such as files, at the same time. To better understand what that means, we'll look at some kernel structures relating to the implementation of these concepts. You will find the diagrams used here in your course textbook, and can count yourself lucky you don't have to deal with me trying to draw them on a whiteboard. But okay, let's see. The kernel maintains a process table. In that, each process table entry contains a table of file descriptors, which in turn contain the file descriptor flags, which we haven't seen yet, as well as a pointer to a file table entry. In addition to a process table, the kernel also maintains a file table. Each entry contains the file status flags, several of which we've already seen, such as append, for example, the current offset, as well as a pointer to a vnode table. Strictly following the mantra that in computer science all problems can be solved with another layer of indirection, we do not immediately implement the file system logic, but instead provide the vnode, which allows for an abstraction of the file system API. Different file systems include different meta information in the vnode table entry, but for compatibility with the traditional Unix file system, they implement or provide all of the inode information. Don't worry, we'll spend plenty of quality time with the inode and all information stored therein in our next lecture. Anyway, so here's what all this might look like. Again, we see the process table, with each entry pointing to a file table entry, with each of those entries pointing to vnode table entry, which finally contains the inode information, as well as, eventually, a pointer to the actual blocks on disk used for the contents of the file. If a process opens the same file twice, then we'll get data structures as represented here. Note that the file table entries, shown in the middle, are distinct, but pointing to the same vnode table entry on the right. Similarly, if two different processes open the same file, then things might look like so. Now, understanding these kernel structures, let's consider some of the calls we've seen earlier. As we discussed, read and write begin at the current offset and increment the offset upon completion by the number of bytes read or written. If we write data and the resulting offset is larger than the file size, that is, we added data to the file, then we simply copy the current offset to the inode file size. So far so good, but we said that if we use append, then all writes will occur at the end of the file. How does that work? Well, if you open a file in append mode, the file status flags are set accordingly, and whenever we call write, it will first set the current offset to the current file size, then update the current offset, and since by definition the current offset is larger than the file size, also update the file size in the inode. Looking at these data structures, we also see how lseek will work. All it does is manipulate the current offset in the file status table. To seek to the end, lseek will copy the current file size into the offset. Done. To seek to the beginning, simply set the current offset to 0. Note also that lseek is entirely independent of the file size. It does not need to go to the disks and actually fetch information from there. Rather, it operates entirely on the meta information. Alright, but what if we have multiple processes possibly accessing the same files at the same time? Then we quickly require atomic operations. As a reminder, atomic operations are operations that are guaranteed to complete in their entirety without another process being able to interfere or not at all. Let's illustrate the need for such operations. Early versions of Unix didn't have the O_append flag, so if you wanted to append to a file, you'd have to first lseek to the end of the file and then issue your write. You had to complete two operations. What if another process did the same thing at the same time? Let's imagine two processes, both trying to append to their respective buffer contents to the same file. Process 1 wants to append p1 always writes to the end of the file, while process 2 wants to append not true, this time p2 wins, p1 loses, haha. So let's pretend process 1 gets the CPU first and begins by calling lseek 0 seekend. As we discussed, this copies the current file size to the current offset in the file table entry of process 1. But now the scheduler decides that it's time for process 2 to get the CPU, and that process calls lseek 0 seekend. So of course it copies the current file size, 128, to the current offset of process 2's file table entry. Process 2 then issues its write, successfully appending data to the end. The new offset is now 173, and since that's larger than 128, it copies 173 to the file size in the inode. Content with having written its data, process 2 happily exits. Now process 1 gets the CPU again, continuing where it left off, which was right after it had called lseek. So with its current offset set to 128, it will write the contents of buff1 at position 128, overriding the bytes previously written by process 2. It adjusts its offset and exits, and we are left with corrupted data at the end of the file. This illustrates the necessity for an atomic operation to append data, and the file status flag O_append solves this problem. But sometimes we want to write data to a different location besides the end, and we want to avoid the race condition we just explained, as that would apply equally for multiple processes trying to do that at the same time too. So to address that problem, we have, in addition to the standard read and write system calls, the functions pread and pewrite, which work just like the normal read and write calls, but take an additional parameter, an offset to which they will atomically seek before issuing the read and write operation. The current file offset will then not be changed, meaning that after a call to these functions, your current position in the file is the same as before you made the call. As usual, if an error is encountered, these functions return -1 and set erno as we'd expect. Let's look at the various file status flags, and what they mean in practice when we run commands in the shell. As we know, when we use the greater than symbol in the shell to redirect standout into a file, it will create the file if it does not exist, and write data into it. If the file does exist, then it will be truncated, meaning that the open flags used by the shell here are ocreate and otrunc. So no surprise, the contents of the file will be overwritten. If we want to append to the file, the shell allows us to do so via two greater symbols, changing otrunc to O_append. Note, however, that even in O_append mode, we are still creating the file if it doesn't exist, so ocreate remains in place. Appending to an existing file works as expected, without truncation of the file. Okay, now let's look at output redirection of multiple streams. If we run a program, we know that both standardout and standard are connected to the terminal. We will get both the error message as well as the output from the command on the terminal. If we want to suppress the error messages, we can redirect standard file descriptor 2 to another file. Using the special device dev-null, we are able to ditch the output from standard completely, but the redirection here is still done simply by opening a file. If we redirect file descriptor 1, standard out then, we don't have to specify the file descriptor. The shell lets us use greater than by itself. Standard will still remain connected to the terminal as we expect. But now look at the contents of file. Note here that ls told us that file is 0 bytes in size. Let's compare. The file is 51 bytes in size. Why did it write 0 bytes in size when we redirected the output? The reason for that is, as noted just a minute ago, that output redirection opens the file in question with otrunc. The output redirection happens in the shell before the ls command is executed, so the shell truncates the file, and when ls looks at it, it finds it to be 0 bytes in size. Okay, let's try to capture standard in the same file. Let's simply redirect it over here using this syntax. When we run the command, we get no output on the terminal, since we redirected both standard out and standard to the file. But what's this now? File only contains the output from standard out of the command. Where did the output from standard go? Let's take a look at the error message. Over here. It is a bit shorter than the output from standard out. Let's generate it again and compare. This is the error message, and this is what we expect to show up in the file. This is longer. So it seems that perhaps standard was written to the file first, but then standard out overrode the output, just like we had illustrated a few minutes ago with regards to o_append being atomic. To test this hypothesis, let's try to generate a longer error message. If we try to ls two non-existent directories, then our error messages are longer than the successful output of the command. Let's give that a try. Interesting. We get a partial error message. So this confirms our hypothesis. Both redirections of standard out and standard open the file in otrunc mode, so set both the size and current offset to 0. The error messages are written, and when standard out is written, it overwrites some of the bytes from standard with the remainder of the bytes from standard being left afterwards. So let's try to fix this by asking standard to use o_append. Unfortunately, that too fails. Standard out redirection opens the file in truncate mode. Standard opens it in o_append mode. But if standard writes data first, then o_append doesn't help us. Let's try the other way around. There, that looks better. So we observed exactly the race condition we illustrated earlier, and we observed that standard appears to complete before standard out. Is that always the case? Well, in general, messages to standard are unbuffered, while I/O to standard out is likely to be buffered, which is why you will likely see error messages prior to normal output when both are connected to a terminal. But of course, there's a better way to ensure standard and standard out go to the same place, and I'm sure many of you have used it before. The easier way to do this is to not tell the shell put standard out into file and put standard into file, but rather put standard out into file and put standard wherever standard out currently points to. This is the common syntax for that. There we go. The advantage of this syntax is that we can tell the shell to put standard error wherever standard out is regardless of where standard out goes to. The most common use case is to tell the shell to make sure to write both standard out and standard error into a pipe. As we discussed, and by design, standard error remains connected to the terminal when you pipe output into another command. So this syntax says open a pipe and connect standard out from the first command to standard in of the second command. Then redirect standard error of the first command to wherever standard out goes to. Oh, that goes into the pipe? Okay, put standard error over there too. But how do we do this? Redirection via greater than and via greater than use the open system call. But how do we open whatever standard out is? The answer to that question is dupe. The dupe system call duplicates an existing file descriptor, and you get back a second file handle pointing to the same file table entry as the first one. Here, let's again look at the kernel structures involved. Note the difference in scope of the file descriptor flags on the left in the process table and the file status flags in the middle in the file table. Unlike in the case where a process has called open on the same files multiple times and gets back file descriptors pointing to distinct file table entries that then point to the same vnode table entry, here we have duplicate file descriptor pointing to the same file table entry, meaning the two share the offset and file status flags, etc. The new file descriptor is indeed a duplicate of the original. Now to allow for redirection of an existing file descriptor, we can use dupe2. The existing file descriptor will be closed and instead pointed to the original's file table entry. In code, this looks like so. Here, we define two messages, one intended for standard out and one for standard error. Our writeBoth function will write the given marker to standard out, and then write the standard out message to the standard out file descriptor, and the standard error message to the standard error file descriptor. In main, we call writeBoth, then dupe standard error onto standard out. That is, we are redirecting any messages to be sent to standard error to wherever standard out currently goes, and then we call writeBoth again. Let's run it. Okay, no surprises here. We have both standard out and standard error connected to the terminal, so the output is sequential and exactly as we'd expect. Now, let's suppress standard error by redirecting it to dev null. Note that in our first call, standard error was suppressed, because our shell had redirected it to dev null. But then we redirected standard error from wherever it was pointing to now go to wherever standard out goes to, the terminal, and so the error message from our second call to writeBoth was displayed on the terminal. How about the other way around? Let's redirect standard out to a file. Now we see an error message on the terminal, and the contents of the file show that that error message came from the first call to writeBoth, when standard error was still connected to the terminal by default. After we redirect standard error to standard out, the write to standard error ended up in the file. This illustrates how dupe2 is used to perform output redirection by the shell, and is another example of how we can easily confirm our understanding by writing a few lines of code. With the visual representation of the kernel objects, we've seen that the file descriptor flags are found in the process table entry, and file status flags are available in the file table. These are usually set when open is called, But what if we want to inspect or change them when we didn't call open ourselves? That is, when all we have is a file descriptor. Enter fcontrol. Fcontrol is one of those catch-all functions that can do a whole bunch of things. For example, you can get or set either of these flags, but you can also duplicate a file descriptor via fcontrol, as well as do a number of OS-specific things. Check your manual page as usual. Let's look at an example of using fcontrol. Here we have another version of our simple cat program. Only in this version we want to ensure that I/O is done synchronously. As a reminder, synchronous output will wait for I/O to be flushed to disk after each call, while asynchronous output allows the OS to handle this more efficiently and cache I/O a bit. Since our simple cat operates in standard-in file now, we can't call open with osync to turn on synchronous mode, as would be done for normal files, so instead we use fcontrol here. To set a specific flag, we first must get the existing flags, then turn on or off whichever flag we want, and then set the flags. The remainder of the program remains the same as before. Okay, before we run it, we'll create a large enough file to illustrate the performance difference between synchronous and asynchronous mode. Let's make it a 10 meg file. Okay, now when we run our synchronous cat, we observe that it takes some time to complete. 4.5 seconds. Now, how does that compare to asynchronous mode? Let's briefly comment out the osync flag, and then run it again. Alright, that was a bit faster, wasn't it? So, synchronous mode guarantees that I/O is flushed right away, but will obviously take a performance penalty. We can turn on synchronous mode by using fcontrol to set the appropriate file flags. Next, there's ioctl. Ioctl is another catch-all function. On UNIX, many interfaces have been shoehorned into the file descriptor API, and things that aren't files at all may have certain flags or other type or device-specific settings. The ioctl system call is often used to tickle those flags for things like terminal I/O, magnetic tape, etc. We mention this here for completeness' sake only, but you are encouraged to read the various manual pages, as you will encounter ioctls when you move on to more advanced systems programming. Finally, given that the file API in UNIX is rather handy, let's take a look at file descriptors being represented as files. I know, it seems like an Inception kind of thing, doesn't it? Anyway, many Unix versions support the def standard-in, def standard-out, and def standard-er devices in the file system to let you access standard-in, standard-out, and standard-er respectively. On our reference platform, these are represented as character devices and can be used in place of a regular file name. This allows you to write a program that processes files as well as standard input, for example, by specifying def standard-in as the path name to open. To illustrate this, let's create two files and trick cat to display the standard input in between those two files, like so. Here we see that cat processes files in order from left to right, first displaying the contents of the first file, then contents of def standard-in, which it now gets from the pipe, then contents of the file third. An alternative way of referencing standard-in via a path name may be the use of /def/fd0, another path name representation of file descriptor 0. Well, what do those things look like? Let's look under defd. Similar to defstandardin, there are character devices connected to your terminal. So far so good. Let's compare two other Unix versions once more. First, macOS again. On this system, defstandardin, etc. are symlinks to defd0, 1, and 2 respectively. But what does defd look like? Here, defd represents the open file descriptors of the current process, so of course we expect to see fd0, 1, and 2 to be connected to the terminal. But we also see two additional file descriptors of type directory. Let's find out what those are. Let's look at the inode number of the current working directory, as well as that of defd. Then let's look again at the contents of defd, but this time also display the inode numbers of the files shown there. We note that fd0, 1, and 2 are all the same inode. They are connected to the same thing, our terminal. File descriptor 3 is connected to inode number 393238, which appears to be the current working directory, and file descriptor 4, inode 318, is the directory defd. All of this makes sense, since every process has a current working directory which it has a handle on. We asked the ls command to list the contents of defd, so of course it has a file handle on that too. Now, what happens when we create a pipeline? Looks like we have just about the same file descriptors open, but this time file descriptor 1, standard out, is of type FIFO, a named pipe. If we redirect standard into the pipe as well, then we should not be surprised to also see fd2 become a FIFO, which appears to be how this operating system happens to implement the shell pipe. Okay, next, let's take a look at Linux again. Here, defstandardin, etc. are also symlinks, but to something called /proc self-fd. /proc is the mount point for procfs, a pseudo file system that allows for a number of process-specific properties to manifest in the file system. To confirm, defd points to proc self-fd as well. In it, we find file descriptors when we list them. In it, we find file descriptors 0, 1, and 2 pointing to terminals, and another entry pointing at proc 8461fd, with 8461 being the process ID of the ls command. What happens if we use a pipe here? Look at that. File descriptor 1 becomes a socket. Looks like this operating system implements the shell pipe as a socket or a socket pair. We'll see those together with FIFOs and pipes in our lecture on interprocess communication again in much more detail. Now notice that the process ID changed in between invocations. which is expected as every command gets its own process. Where is the process ID of our current shell? $84.50. So let's look at this shell's currently open file descriptors. As before, fd0, 1, and 2 are connected to the terminal, and then looks like this shell has a file handle open to a shell history file. Many shells, by default, log all commands entered into a history file, so it's no surprise that the shell has that file handle open. Now, finally, let's take a look at why it might matter how a shell implements a pipe. Previously, we were able to use the path name defstandardin to fill in when processing files in a pipeline. Def-fd0, which defstandardin points to, behaves as expected when connected to a terminal. But when we try to use it in a pipe, we get a weird error, defstandardin, no such device or address. This is because, as we saw above, Linux appears to implement the pipe using sockets, but you can't open a socket. We have other system calls for handling sockets. But the cat command knows nothing about sockets. It's been given a path name, defstandardin, and tries to open that path name, which now fails. This is a reminder that even though different Unix systems behave similarly and ought to follow the same semantics, sometimes things break or behave in unexpected ways based on how somebody chose to implement a certain feature. Alright, this, finally, gets us to the end of our Week 2 materials. In this series of video segment, we've covered in some detail all of the 5 syscalls used for almost all Unix file I.O. We've run a number of code examples to clarify our understanding and illustrate certain, perhaps surprising aspects. There are a few additional links in the PDF of these slides, so please do make sure to check those out. But with all this, you're now more than ready to finally put your knowledge to the test, and I've posted the first homework assignment linked here. We'll discuss the assignment in more detail in class. In our next lecture, we'll move on to files and directories, where we'll spend a fair bit of quality time with our new friend, the struct stat. Until then, thanks for watching. Cheers!